So we're going to be going over exclusive OR and exclusive NOR gates. Before we get into that, guys, I'd like to go ahead and make the announcement that next week y'all need to be coming on campus so we can start knocking out labs. Okay?
Yes, ma'am. Yes, ma'am.
So we should be able to fit everybody in the classroom, so everybody should be able to get on campus. And we will be going right into lab to do a lot of the experiments we need to do with this stuff to kind of give y'all understanding of how this all works. So we have combination logic circuits. And these guys are used very often, so they have their own symbol. So we have digital comparators, parity generators, and checkers, binary adders. They have several different places they use just about any of this. So this should look familiar. Why should it look familiar?
That's what we were doing last class.
It's what we were doing in the last class where we were looking at how ands and ors and nots all work together. So let's say, so first of all, what is the symbol? If this has a little circle on the top part of it, what does that mean?
It's an inverter.
It inverts the output signal, yes. The output signal is inverted from the input signal. Okay. What do the little bubbles mean if they're on the back end of it?
It's inverted before it goes in.
It's inverted before it goes in, very much. Does it make sense to everybody?
Yes, ma'am.
All right. So for figure A, we have what kind of gates?
Or and.
Well, that is an OR, but these are what?
And gates.
NAND gates, yes. NAND. Okay.
So when they're inverted, they're NAND.
When they're inverted on the output side, yes. Okay. So then this one has inverted AND gates because the signal's coming through inverted on the front end, not the back end. Anybody see that? Okay. So these are all AND gates. We just inverted the signal from whenever we put it in. This one got, so what about this one, guys?
This is the first one, an AND gate.
This first one is an AND gate. What's the other one? Or what are the other two?
A NOR and an OR.
A NOR and an OR. Everybody see that?
Yes, ma'am.
All right. All right. And then lastly, these are what? The last three are NAND and NOR gates. You have a NAND gate and then you have two NOR gates. Okay. So all this is really just trying to show you some different configurations. So let's talk about exclusive OR gates. So exclusive OR gates. Okay. So if both inputs are the same, the output will be low. So in other words, if we treat this like an AND gate, you will not get an output. If the inputs are different, the output will be high. So for this particular truth table, hold on real quick, guys. Okay, so the truth table for this one is going to look a little something like this. So signal 1, signal 2, and then signal out. So we go 0, 0, 0, 1, 0, 1, 0, 1, 0, and then 1, 1, 0. I'm sorry, there's one of those that's supposed to be a 1. Does everybody see that? Okay. So if the inputs are different, the output will be high. If they're the same, the output will be low. Okay. So for signals A and B, if I use it as a OR gate, then anytime I've got a high, I get an output. So these are two lows, and it makes a low. You'll see that? So then this guy goes high. At the same time, this will go high. And then this guy goes low, but this one stays high. I'm sorry, goes high, and you get another signal out of it. See where I'm kind of going with this? So then you come to this one right here, and both these signals are high, or they're on, or you want to call it. And it's not until the signal drops on one of these that I get an output. Does that make sense?
Yes, ma'am.
So here we go. Anytime you have double up, you end up without an output. The only time you're going to get an input is if you're putting input on either one or the other of the system. Okay. So for an exclusive NOR gate, logic, so it's a complement to the exclusive OR, which we just went over. So this one should look, again, very familiar. Okay, so we have an exclusive NOR, which is the opposite of the exclusive OR. With the exclusive NOR, you have to have double digits to get an output. An exclusive OR, you need to have one output and no other, I'm sorry, you have no, I'm saying this badly. To get an output in exclusive OR, you can only have one signal at a time. Does that make sense?
Yes, ma'am.
Okay. Excuse me. So electrical noise in the transmission of binary information can cause errors. So what do they mean by that? It's the fact that your computer, what is it thinking? How is a computer programmed, guys?
Ones and zeros?
Ones and zeros. So this is why it's so easy for something to get messed up in these programs, is because of this. It's very easy for it to switch ones and zeros around because you happen to be the one that's not paying attention to what's going on. Does that make sense? So electrical noise in the transmission of binary information can cause errors. This is something that can cause your computer to crash. It can cause a lot of other problems. Okay? So Parity can detect these type of errors. Okay? So you have a couple of different ones. You have odd and even parity. It adds a bit to the binary information. So we'll kind of go into it here in a second. All right, so just to kind of give you a bit of what this worksheet is supposed to look like. I know y'all probably, I don't know if y'all can access it or not. Let me double check something. All right, guys, give me just a second. I'm going to pause this. All right, so this is the worksheet that this thing is mentioning. Excuse me. So what it should be is to draw the X output for a exclusive OR gate given the state of A and B inputs. Okay. So the very first one, let me see if I can. Okay. Go back to what it was. All right, so for the very first one, what should my output look like? I also draw my output on this. What should my waveform look like for an exclusive OR gate if this is what I'm given? Anybody want to take a guess?
I'm lost.
All right, so for an exclusive OR gate, what was it? What was the truth table? The truth table is that two signals that are the same will not produce an output signal. Okay. So for this particular one, I start off with a high that goes for about 2 bars, then it goes down and goes low for 2, and then it goes up and out. The one under it starts out low, then it goes high for 1. I'm sorry, it goes high for most of this until it gets to the end where it goes low. Now, the truth table was that to get your output, switch to, if I have 2 of the same inputs, I will get no output. However, if mine are different, okay? So if I were to draw this for X, I would get a signal here, I would drop it till I got to about here. It would go back up, continue all the way down here, and then actually it just goes all the way out. So the only time the signal is going to drop is when both of these go high. Does that make sense? Does that make sense to everybody?
I mean, I get it, but not really when it comes to the drawings.
Okay. So,
So, like, when they're both high, it's are they both like going the same direction, or are they going towards each other?
I'm not quite sure I know what you mean, but what you're looking for a exclusive OR gate is for two signals to be the same. That means you're going to get no signal. So it'd be like two people trying to talk over each other. So if two people are trying to talk over each other, they're not going to get any input or output from each other, right? On the other hand, if one is allowed to talk, the conversation can move forward. Does it make sense?
Yep.
So that's what this is. What this is it's two people in a conversation, but in this case, it doesn't want to overshout their friend. So that's why you end up with an exclusive OR signal. So what about for this one?
So with these, they're different signals. One is A is high, B is low. My question is, which one will be the output at that point? With A being high and B is low, they're obviously allowing one to talk, but which one is talking?
Very good. So what you're looking at with this is where are my signals different? So I would have a high signal here up until I got to column 2, then it would go low. Why? It would go low because
Hold on, how is column 2 low? It looks like column two is column 2 where it says 2?
yes,
Then,
so column 1, you have two different outputs coming through right now.
yeah,
So
high
that
and
means
low, I see that.
They're the same, right?
yes, for 2
Yeah,
they're
that's
the
what I'm
exact
saying.
same. You have two high signals instead of a high and a low.
That's what I found out where I was getting confused, because I was looking at the whole thing as a whole versus each section.
Now you gotta look section by section. You gotta look section by section for this.
Okay, so section 1, you have a high and a low. Section 2, they're the same, so it cancels out. You can't do anything because they're both talking at the same time in that case, right?
Yes.
Section 3, they're both low, so they're both talking again at the same time. But section 4, you have a low and a high. So my question is, if you have a low and a, let's go back to 1. You have a high and a low. Which one is talking? Which one gets the floor?
Okay, so for the first one, you had a high at one in column 1 because you have two different signals. It dropped for column 2 and went high again for 3 and 4 and 5. The whole reason that happened is because you've got these signals right here that are high for both of them, but then A drops low. Does everybody see that?
I'm not gonna lie.
Steve,
Me thinking in high and low was messing me up, and this until I just converted it to ones and zeros, because that's how I know this is ones and
Mhm.
zeros. Because PLCs is just it's a lot more simplistic.
Well, that's pretty much what this is. I'm just trying to use the terminology they keep trying to use in the questions. So if you want to think about it like PLCs, A is 1, B is 0. Then A and B are both 1, and then they go back to one having, this one goes to A being 0, while
Yeah,
B is
that
remaining as
100%
1.
helps me.
So what you're looking for is for differential, you're looking for signals that are not the same. Okay? Because it's when the signals that are the same that you have the problem of it being off. Does it make sense?
Yes, ma'am.
So for this one, I start off with a 1 on A and a 0 on B. Then both of them go to 1 and 1. A drops to 0, B drops to 0, so that's going to be a 0 output. Then you get a 1 output because B goes high while A stays low. You get a 1 output here because the A goes high and B goes low. That's essentially what you're looking for, is where is the differences in signal. Because when they're in the when they are similar is where you're going to have it tangle up. Does that make sense?
Yes, ma'am.
so in this case, how would the X output waveform look?
So for the second one,
Yeah, if we had to, because you got to draw it, you know. How would that drawing look?
okay, so let me go back to a whiteboard here. So A goes high for 2 bars, dips low for 2, and then it goes high for 1. B is low for 1, goes high for 2, goes low for 3, high for 4, and then low for 5. So my output signal would look like this. Let me get a different color. So it would be high for 1, low for 2 and 3, high for 4, and 5. So that would be your output. Does that make kind of sense?
I have to. Let me see.
So let me put it to you this
back
way.
to-
So this is a 1, this is a 0, and this is still a 1, this one becomes a 1. And you get a 0 and a 0, a 0 and a 1. So this is going to be a 1 and a 0.
Okay.
So my output
follow.
becomes 1, 0, 0, 1, 1.
I see what bro was saying now. That makes a lot more sense.
Yeah, that clarifies a lot.
Sorry,
Yeah.
I keep
I
trying to
thought
figure
you
out how
would
to
have to go
explain
through-
it better, but
Well,
yeah.
like my problem is that I've had Rich, like because I had him in PLCs, I'm still thinking in that mindset. So like, I don't know how to explain.
It's fine. Believe you me, I understand what you're saying.
It's like two different concepts. They're saying the same thing, but like it's a foreign language, like someone speaking in a foreign language to me.
I understand. That's why I keep trying to make sure y'all understand this. It's not easy to kind of jump in on some of this. So I'm trying to figure out how I can better explain it to help y'all understand it.
Yeah, I think this part right here definitely helps out way more.
I'm glad I can help. All right, so let's look at the third one here. So this one is a zero, it starts off at 0 for A. I wish I could draw on this, but it's not going to let me. But you start off with a 1 at, with a 0 at A, a 1 at B. A 1 at A, a 1 at B, a 0 to a 1, a 0 to a 1, and then a 1 to a 0. So this one's going to have a lot of output to it. So to show you again on that whiteboard, you start off low, high, low, low, high. For your other one, you start off high all the way down until it switches to low, or ones and zeros. So this is a 0, this is a 1, this is a 1, this is a 1, this is a 0 and a 0, this is a 1 and a 1, and this one becomes a 1, this one's a 0. So my signal output should be high to a low to a high all the way down, and that's it.
Got it. That makes sense. I see it now. Cool. And we need to do this. I assume we got to do this worksheet and turn it into you next week. Is that kind of the gist of things, or we just doing it together?
I'm just kind of letting y'all do it together with me so that we can kind of make sure everybody's on the same page.
Gotcha.
So I just kind of want to make sure everybody's on the same page before we move forward. All right, so looking at the next one, I'm going to go ahead and just draw it, and that way we don't have to keep bouncing back and forth here. So the signal starts high for 2 bars, then it goes low for 1, high for 1, and then goes out low. I'm sorry about the crappy drawings, guys. I'm trying to do this with a mouse. It's not exactly precision instruments. So that starts high, goes low for 2, then it goes high for 2. So let's go back and observe. So we've got a 1 and a 1, a 1 and a 0 and a 0, a 1 and a 1, and a 0 and a 1. So my output signal, all right, my output signal should be low, high, low, low, high. Y'all see what I just did?
Yeah, I see it. Because the 1 cancels out, makes it 0, which is a low. The 1 and 0 makes it a high. 0, 0, obviously low. 1 and 1, obviously low. And 0 and 1 will make it another high. So
Yes. Yeah. You're looking for opposites.
Like totally. Yeah, like a high makes a high. Okay.
Okay. All right. So before we go to the next set, we're going to be doing exclusive NOR. Y'all got any questions on this one? And I think this is out there for y'all to use. If it's not, I will make sure it gets put out there. But you should be able to try and find this out there. If it's not there, let me know. Have y'all got any questions on it so far?
No, ma'am.
Nobody's got any questions whatsoever?
No, ma'am.
All right. So before we go to the exclusive NOR, I'm gonna say let's go ahead and take about a 5 to 10 minute break, guys. That way we don't shove too much at you right now. All right. So if the exclusive OR gate is looking for differences, then the exclusive NOR gate is looking for similarities. So in other words, if you remember, the truth table for this was for every time you have the same signal for both, you end up with an output. And every time your signal has differences, you end up with no output. Does that make sense?
Yeah.
Okay, so this guy's just the opposite. So where we were looking for difference in inputs, now we're looking at differences. We're looking for similarities in inputs. So looking at this first one, what do I know my first column will be?
1.
It'll be a 1. That's right. What about the second?
0.
No, actually,
Well, 1. I'm sorry, it'd be a 1, right? If they're the same, it's a 1, right?
yes. So you would end up with, let me redraw this for y'all real quick. So we got a high or a 1. You get a 0, 1, 0, 1. For the input for B, you get a 1 and then a 0 all the way down until you get to the end and you get a 1 here. So my output should look more like this. I might grab a different color. So we said it was going to be high for 1. So it'll be a 1 for 2 as well. So this is a 1, this is a 1, 0, 0, 1, 0, 0, 0, 1, 1. So I'm going to dip at 3. I'm going to get a signal for 4 and for 5. Y'all see what I mean by that?
So you only dip it when it's different.
For this one, yes. For this particular one, you dip it whenever this there's difference in signals. Does it make sense?
Yes, ma'am.
Okay. So for the second one, for this one right here, what would my signal output look like?
Should be 1, 0, 0, 0, 0.
You're right. It should be 1, and then the rest of these are all zeros because you have opposite words are not my friend today, apparently. So you're going to have all zeros for the rest of these because they are not the same signal. You don't have two highs or two lows. You've got a high and a low, high, low, high, low, and then a low, high. So you will have a difference of signal with those. Okay? Does that make sense to everybody?
Yes, ma'am.
Okay. So what about for this last one? Let me stretch it out a little bit.
One, 0, 0, 0.
So this one actually would be 1, 1, 0, 0, 1. Now you probably
Okay,
ask,
I see it now. That was kind of weird.
all right. So that is the actual order, is it's supposed to be 1, 1, 0, 0, 1. So there you go. Any questions on these, guys? All right. So that was that worksheet, and I just kind of wanted to work that with y'all. So with parity generators and checkers, we're looking for errors that would indicate problems with your output. We have a specific integrated circuit that we use for this as well. And that is the 74280. So what they're trying to, this is figure 6-9, which is supposed to be even and odd parity generators. So you're looking at exclusive OR gates. Okay. So when we have exclusive OR gates, what are we looking for?
You're looking for the ones that don't match.
You're looking for ones that don't match. Okay. You're looking for ones that don't match. Make sense? Okay. So this is looking to get, so this has two signals. So this is looking to have, so this one I would hope would have an output. So this would mean that these would have to have two different inputs. So once this output is put into the next one, we have to make sure that this guy has no output, so I can have output come through. I'm sorry, it doesn't have any input. Or if this has input, this guy can't have output. And then it ties back into the last one, and it goes from there. Sorry. So with these specific chips, they have 9 inputs. So we work the 9th one as a ground so that it won't affect results. Because what you are always looking for is a good, steady signal. Okay. This will probably make a lot more sense once we get into lab. All right. So parity is looking for that equal, looking for signals. We're looking for either an even signal or an odd signal, but we're looking for some form of the signal to be steady when we're working with these. That's why we tie off unused inputs so that we don't end up with a signal that won't work correctly. Okay. So using these chips, we're able to create, I said words aren't coming well to me today, guys, so you'll have to excuse me. So this is looking for errors in the parity, or in the state of everything being equal out and being steady. So you've got your inputs all on this side. This side has your outputs. And if you notice, they've tied the outputs of one to the outputs of the other. They're getting signals from these receivers and this computer to tell them what to do. And then this guy's sending that extra signal over to this one to either give him an indicator that there's an error or one that's not an error. If that makes any sense at all, guys. As you notice, the 8th port on the first one is tied off to ground. That's just to kind of keep it out of the way, since we don't need it. Okay. So we're looking at another setup here. So these are exclusive NOR gates. So what are we looking for with exclusive NOR gates? What exactly are we supposed to be looking for here? You're looking for signals that are supposed to be the exact same. You're looking for either 2 highs or 2 ones rather, or you're looking for 2 zeros or 2 lows. So this one is comparing a comparator. I'm sorry. It's comparing these 2 binary strings. If they're equal, they'll give a output. If they are unequal, they will not give an output. So this one, they have it tied to a buzzer, so that whenever they are in agreement, the buzzer will sound. When they are in a disagreement, the buzzer will not sound at all. If that makes any kind of sense. So if you look and kind of try and follow the spaghetti here, they have each one tied together. So A0, B0, A1, B1, A2, B2, A3, B3. So it's comparing string A to string B down the whole line here. And then everything goes to what kind of a, what is this, guys?
And
It's an AND gate, which means what?
it needs two inputs.
In this case, you need a minimum, I believe, of 2 inputs, but so that would mean to be able to get a signal here, what do I need to do to get a positive, to get no signal out of here, is have these guys be totally different, right? My signals have to be different for this guy to pass. No, I'm sorry, my brain decided to check that one out. So in order to get a 1 here, since this is an exclusive NOR, both signals have to be the same. So that means that in order for this to come on, your signals have to be the same for all of these. Okay. So this is a controlled inverter. So we're using binary arithmetic circuits to control a signal. Excuse me. Design an 8. So this is a 8-bit controlled inverter to receive a signal that, if high, causes the circuit to complement the 8-bit string, and if low, it does not. So we have an 8-bit string. We want a controlled output. Okay. So if the control signal C is high, these are what? Are these exclusive or exclusive NOR, guys? They're exclusive OR, which means we're looking for what kind of signal?
Hello.
Looking for a low. Because the second any one of these goes high, it's going to change my output, as long as my signal C is high. However, if C is low, then what happens? Then I need to make sure that one of these is high, that these guys go high to be able to create that signal. Does that make sense? Kind of, sort of. So this guy's go ahead.
I just agree.
Okay. All right, so this is a 4-bit comparator. So what are we doing with a comparator is we're comparing 2 or more things to see if they will work together. The best way I can talk this way through right now. So this one has a greater than, less than, or equal to set right here for these 3 pins. So this is what allows us to compare on the output. So then you have these guys tied to making that output work. Excuse me. And this is the internal schematic for this. So you have A3 and B3 that are tied to a what kind of gate?
And
It's a what now? So this guy right here is actually a NAND gate, right? How can I tell? Because he's an AND, but he has an inverted output. I know that because of this little bubble right there that it's at the tip. Okay. So then we go, it feeds out to two AND gates and a NOR gate. Now, how do I know that's not an exclusive NOR?
Is it because one's high and one's low?
Well, it's also because in the symbol itself, it should, if it was an exclusive NOR, it'd have that little slash on the back end of it. That's what is indicating that exclusive NOR. But this is just a NOR in and of itself, which means that any inputs you put into it are going to be negative on the output. Okay. And then the way it comes out of this signal is it goes and feeds into another AND gate, rather a couple of them here as well. And then we are able to, with this, get outputs that are three different ways. We are either comparing A to B, as in it's greater than, it's looking for equal to, or it's looking for less than on the output. Okay.
Could this be simplified?
In this case, this is all inside of a singular chip, a singular microchip or integrated circuit chip. Technically, there are ways that you might be able to simplify this. However, in doing so, you would not be able to use the chip itself there, since it's all built in. Does that make sense?
Isn't it like just the chip's multi-purpose? Like you can use the chip for different things.
Yes. So you don't have to use every port in these chips. Let's say I'm looking for two signals. I have a signal A and a signal B. And I'm wanting to compare that signal. So what I can do is, whenever I put this together and put these signals in, I also need to make sure that I put in for the calculation I'm looking for. So again, this is all just allowing it to compare and contrast the circuit so that it will, the output it gives you is in the state that you are trying to make it work for. I probably am not saying this very well or very right, but I'm trying to see if I can figure out how to say this better. You're essentially just trying to compare signals. That's all you're really doing, is comparing two signals together so that if you're trying to send a signal to from your remote to your TV, you know, are you trying to turn the volume up or trying to turn it down? Or if you've got two push buttons, or you've got two load sensors, that one would probably be the best one here. If you've got two load sensors and you're looking to try and make everything either equal, or you're trying to create a different kind of balance. Does that make sense? So you're trying to create a type of balance with this so that it, when you look at your output signal, you actually can see the differences between them. So if I have two train cars full of something like flour or full of gasoline, I might be looking to see which one is greater or lesser, or I could be just trying to make sure that they both end up equaled out so that I can create a log of it and send it down the road. I mean, there's a lot of different ways you would use something like this, guys. So it's all depends on exactly what you're looking for and how you're trying to get to use this. If that makes any sense at all. Okay. So again, you're trying to compare signals here again. This is looking at the result on the output over here. What they've done is they've connected these so where the outputs here are looking at the outputs, or feeding into the outputs, into the, they're not outputs, they are inputs to help with the comparison for the different pieces. So the first thing they've got is A1 to A0 through 3, and they have 4 through 7, and same for B. So what they're doing is they're trying to compare A to B with these different inputs. All right, so I'm not sure where some of these slides have gone, guys. So looking at this, once again, we have an exclusive OR, which means we're looking at what?
The different signals.
You're looking for two different signals. So you're looking for two different signals. So you're actually tied into this AND gate as well. So the signal for A will go to both the exclusive OR and the AND gate. Then B goes as well. So if I have a high on A, I have a 1 on A, and I have a 0 on B, which one of these is going to turn on? Or which one of these will allow it to flow?
Say that again.
So if I have a 1 signal on A and a 0 signal on B, which one of these will allow a signal to move through? So it would actually, so the exclusive, this means that this guy right here would allow that signal through. Because in order to get a signal through an AND gate, what do I have to do?
both of them have to be the same.
Both signals have to be the same.
Oh,
Both signals have to be high. If I have this signal right here, a 1 and a 1, that means that this guy will allow flow. If I have a 0 and a 1 in whatever combination, that means that this guy allows flow. However, if I have 2 zeros, that means everything turns off and it doesn't work. Because an AND gate must have 2 positive signals to allow flow. Correct?
Yes, ma'am.
All right, so looking at this guy, so you're again looking at different ways that these guys are being used. So this one is again tied to the AND gate. It's tied to an exclusive OR gate. And the outputs for the AND go to an OR gate. The output for the exclusive OR gate goes to an AND gate and another exclusive OR gate. So what does that mean for our signal? So if I have a 1 and a 0 at A and B, that means I'm not going to get a signal through this guy. You can just forget him, right? I'm going to go through this guy, and I'm going to be able to put up what kind of a signal out? Is it going to be a positive signal or a negative signal?
Positive? Wait. No, negative.
It will be a, well, if I have a 1 and a 0, I get a positive output. I get a 1. And this guy has to have a 1 here and a 1 here to allow flow. So that means that this guy has to have an output of 1. Everybody following so far? So in order for this guy to pass a signal, it means that this guy will not. If I want this guy to pass a signal, then either this guy can't or this guy can't. Because that's an exclusive what? This is an exclusive OR gate. So in other words, for this guy to pass a signal, okay, I need to either go through this one by having A and B become positive. I have to have A or B become 1 and a 0 to allow my exclusive OR gate to pass. And then I have to have C as a high. So I can have something like that. I could have something along the lines of this. But C would have to have a signal of some sort. Okay? Does everybody see what I'm saying?
I'm kind of lost.
Okay,
to be
so let
honest.
me try
I
this
may have to
again.
review this video after. But
So
yeah.
let's say I've got a positive and a a signal on A and a signal on B. In order for this guy right here to pass the signal, I have to have a signal at C. So what that will do is that I will end up getting a signal here, which gives me a signal out. However, this guy is also tied to this input, and AND gates do what?
They gotta have both signals to work.
It has to have two, at least one, it has to have two signals to work, excuse me. So in order for him to pass the signal, I have to have a signal here, which that will bring that up to him. So then he will pass it to this OR gate and you get your signal out. However, if you want, well, not so much want, but in order to make this guy work, it would be kind of a shortcut. You'd have to have a signal, two input signals, so you could get an output here. But what that will do is put this at a 0 for an output. So that can actually trigger, if this guy is positive, an output at this guy. In any way to use this one right here, I either have to have a 0 coming from this one and a 1 from this one, or I have to have a 1 from here and no signal from C. Does that make sense, guys?
Yeah, I got that. That makes sense.
Yeah, it's a little bit easier to understand these when you like highlight where they're supposed to go.
Yep. So the signals on these, this guy has to depend on signals A, B, and C to let the signal pass through him. He just has to rely on signals A and B to allow the signal out here. For this guy, he relies on the signals from A, B, and C to allow passage. That makes enough sense for y'all. I said I'm trying to put this in a way that's not sounding like total gibberish. Does that make a little more sense though?
Yes, ma'am.
Okay. So if I was to ask one of y'all to trace A, what kind of signal inputs am I needing to use for the A?
Should be the same signal.
So I have to have a signal at A, is what you're saying? Because what you
Yeah.
have to be careful of is what is A connected to?
A NAND gate.
A NAND gate. What is the logic of a NAND gate?
You get out negatives.
You get out, just to kind of go back to the truth table here, guys. So if I have input 1, input 2, and output, for a NAND gate, go ahead and put the color here as he likes to have zeros, but he does not like to have two positive inputs. For his friend, the AND gate, he likes only positive signals. Okay? So in other words, to trigger this guy, that means that I have to have a signal at I have to have a signal at B and a signal at C that are both positive to allow him to pass anything. What are they connected to?
An exclusive NOR gate.
They're connected to an exclusive NOR gate. So that means he's looking for what? to allow a signal?
Differences.
Not differences.
Wouldn't it be the same?
You have to have the same signal for both sides. That's where this is going to get kind of tricky, right? So with this guy, what we're looking for is I've got to have a signal from this guy, and I have to have a signal from this guy, whether they're positive or negative. I have to have a signal from both. Okay? So I have to have a positive signal here and a positive signal here to allow this guy to give an output of 1. For this guy to give an output, that means that A cannot give an input. Why? Why can A not give an input?
Because if B gives a signal, it can only have one signal coming through. It can't have both.
Exactly. I can't have a signal coming in through A if I'm looking to get an output of 1 from B. I'm sorry, from this guy. So that would give me an output of 1, which would allow this guy to allow flow. Now, what if instead I had no output at C, I have no output at B, but I do have output at A, is that this guy will not allow a signal through, it'd give a 0 signal, and this guy would give a 1 signal. Not really ideal for what we need, right? Because this guy won't let it through if I have mismatched signals. So the only other way that this will let it through would be to what?
To have no output at A.
To have no output at A. Then I would have 2 zeros for my inputs for this guy, which would give me an output. Does that make sense?
Yes.
Okay. Is this all kind of making more sense for y'all?
And when you're at a chart up there.
All right, so looking at B, I'm going to give y'all just a minute to look at it, and then we will discuss it and try and find how we would have to solve this. So I'll give y'all just a minute to kind of take a look at it. All right, so what do I need to do to get an output at Y?
You need to have a signal at A and B and no signal at C.
So I have to have a signal at A, and I have to have a signal at B with no signal at C. So if I do that, that means I have flow from A to my AND gate, B to the AND gate, and I have a positive output here. And that also would continue down and give me a positive output here, correct? So this guy, go ahead.
I was just agreeing.
Okay. So this guy right here is an exclusive what?
Or
It's an exclusive OR. You're correct. So in order for him to get a signal out, does he have to have signals that are the same or signals that are different?
different.
Okay. So that means that C has to have that other input, because this is also tied to a NOR gate, which a NOR gate, what does it want?
The same. You said the
It
NOR?
just wants zeros. So, yep, it can't have any signal at all into it.
All right, for an OR gate, I guess signal only when I've got a signal. For a NOR gate, I only get a signal when there is no signal, right?
Yes, ma'am.
So I've got a positive signal on one side of this NOR gate. That means he's not gonna do what?
Activate.
Means he won't activate. So instead I need, and I'm going to take an eraser to this, and I'm going to show y'all what exactly you need as far as signals for these guys. So knowing my truth table like I do, I have to have no input at A, no input at B, and no input at C. So that means that this guy will give off a negative input, a negative output. That means that what's coming in here is going to be a negative output, or a 0. What comes out of this guy will be a positive output. It'll be a 1. And since this is a negative signal, it's going to tie down to this guy and give him a negative signal. Will that allow flow? Or will that allow my signal out? Might be a better way to say that. And the answer to that is yes, it will allow flow out. Does that make sense, guys? Do y'all see how I did that? Did it make sense? So if I put all positives on these, let me redo that real quick. So if I switch this up and made A positive, B positive, we'll even say C positive. That means that I get a positive output from this guy, which gives a positive output here. But when I put a positive output on this guy, what does that give me out?
A negative.
It gives me a negative, or yeah, it gives me a negative out, excuse me. It gives me a negative out. So that means that this guy will again allow flow. But what if I change the signal up? If I put this guy at a negative and this guy and the other two stayed positive, that means that this guy won't work, right? Because what he'll give out is a 0 or negative. And then I got positive put on this side, which means that this guy will not allow flow. Actually, I'm wrong. That would actually allow signal through, wouldn't it? So if I change this guy to a negative and these guys stayed positive, that means I would get a negative output for this guy. That would mean I've got a positive input for this guy, which would give me a negative output, and a positive input on the other side, which would allow me an output. So this is the kind of thing you have to really play with and understand, guys. As you can see, even I sometimes goof up whenever I'm trying to rush through this. But whatever you're looking to get out of this guy, you need the opposite input from C. Does that make sense? Because in the scenario, if we have let's say we put a negative at C, and that means I would have two negative signals here, which would allow flow, but then I would have a positive and negative symbol here, so again, that would allow flow. I'm confusing myself right now. I'm trying to remember the one we just did that y'all didn't get an output. So whenever you're dealing with these, it does really pay to know which one of these gates does what. So with an AND gate, you have to have the idea of what you're tied into after it. So in this case, we have a NOR gate that's tied to an exclusive OR gate. So knowing your truth table for a NOR for an exclusive OR gate, which again is what? He wants both his signals to be opposite, right? So that's why we end up with this guy, is he's actually inverting the signal. So if he goes positive, you better make sure that whatever's trying to balance it out is what? I did not come up. You need to make sure whatever's coming out the other end is negative, and vice versa. And that way you can get a signal out. Okay. So exclusive OR gates outputs a high if the inputs are not the same, and the outputs are low if the inputs are. The NOR exclusive NOR gate gives a low if the inputs are not the same, and a high if they are. And you can always, in your notes, guys, if you see the word high, think 1. If you see the word low, think 0. Okay? That, or you can think this is going to give you a negative symbol, or a negative signal. This one will give you a positive signal. However you want to think about it. Excuse me. Does that make sense? So a parity bit is commonly used for error detection, either serial or parallel. So exclusive OR and NOR are used as parity checking, binary comparison, controlled complementing circuits, and can be used to perform binary arithmetic or addition. All right, so that is that one, guys. If y'all got any questions, real quick.
Will this be uploaded before the weekend? I plan on